Hello, I'm Maurice Dupre, and in this section we're going to discuss vector functions and their derivatives. Let's look at a picture to begin with which illustrates what a vector function looks like. That is, how we should think of a vector function. We're going to be considering vector functions of a single real variable t, and so as the variable t changes, the vector changes. And so consequently, if we imagine the vector's tail fixed at an origin of a rectangular coordinate system, then as its tip moves through the change in the vector, the tip traces out a point in space. If I think of the variable t as time, then we can think of this vector function as specifying a motion in space, and that's an extremely useful way of thinking of it. For instance, think of a little gnat flying around in space, and at each time t, r of t, the vector r at time t, specifies the position of the gnat relative to a fixed origin. So as the gnat moves in space, his position vector changes. Well, we want to consider things like limits and continuity to start with. For instance, in terms of limits, we want to think of as t approaches a certain time t sub naught, does the position p of t at time t, that is the tip of r of t, does that approach a given position? What does it mean for continuity? Well, continuity should mean that the limit at t naught exists and equals the value of the function there. Let's look at a useful fact about limits of vector functions. The limit as t approaches t sub naught of r of t equals the vector L is the same as saying the limit as t approaches t sub naught of the length of the difference vector r of t minus L, that length equals 0. Notice when I form the length of r of t minus L, I'm getting a numerical function of the numerical variable t, and so consequently this limit is an ordinary numerical limit. And so consequently we can turn problems of vector limits into ordinary limits. Well, what will that mean for us? Notice if the vector has component functions f, g, and h, so r of t is f of t times the unit vector I along the x-axis plus g of t times the unit vector j along the y-axis plus h of t times the unit vector k along the z-axis, and if the vector L is ai plus bj plus ck, when I compute the length of the difference r of t minus L, what I have is f of t minus a square plus g of t minus b square plus h of t minus c square, all raised to the 1/2 power. So from this equation, we can easily see that the limit as t approaches t naught of this expression will be 0 if and only if each of the limits of the components exist and give the values a, b, and c respectively. That is, the limit as t approaches t sub naught of r of t equals L if and only if the limit of t approaches t naught of f of t equals a, the limit as t approaches t naught of g of t equals b, and the limit as t approaches t naught of h of t equals c. That is, all the limits, all three limits must exist, equal the component values of L, A, B, and C respectively. If these limits exist and have these values, then the limit of the vector function exists and equals L. Conversely, if the limit of the vector function exists and equals L, each of these limits exists and have their respective values A, B, and C. Well, since limits for vector-valued functions are computed component-wise, we can see easily that continuity for a vector function is easy to check. A vector-valued function is continuous exactly when its component functions are continuous. What about for differentiation? Let's look at a picture to see what this means. Here in this picture, we have a curve, which is the trace of the motion of this vector r of t. Its tail is fixed at the origin of coordinates. And so when we look at what happens during a change in time from t to t plus delta t, the tip of the vector moves to a new point, r at t plus delta t. So what's the change? Delta r is r at t plus delta t minus r of t. So notice this vector from the tip of r of t to the tip of r at t plus delta t is the delta r. So consequently, what we want to do to differentiate is divide the delta r by the elapsed time delta t. Well, notice for delta t small, dividing by delta t, 1 over delta t will be large, and so it'll stretch that out. And so the picture then looks like this. Here, stretched out is delta r over delta t. In other words, as we let delta t go to 0, this second point moves back to the first, but the delta r over delta t, the ratio tends to a definite limit, and you can see that that limiting vector will be tangent to the curve. So that r prime of t is the limit of delta r over delta t as delta t goes to 0. That will be tangent to the curve. So let's write r prime of t equals the limit as delta t approaches 0 of delta r over delta t. And so as this second point moves back to the first, you see the arrow through those 2 points is going to turn and become tangent to the curve. So consequently, if I'm thinking of the t variable as representing time, then delta r over delta t represents the average velocity during that time interval. And so as delta t approaches 0, we get r prime of t giving the instantaneous velocity of the motion. And so what we see is that the instantaneous velocity is tangential to the curve of motion. Its length gives you the speed at that instant for the motion. So length of r prime of t equals speed. R prime of t equals velocity when we're thinking of t as time. And so consequently, what we see is that our velocity vector in a motion at each instant is tangent to our curve of motion. It tells us in what direction we're going. Well, let's see how we actually calculate derivatives and review some rules. If I have the vector function r of t with component functions f of t, g of t, h of t, so r of t is f times the unit vector I plus g times the unit vector j plus h times the unit vector k, then r prime of t, the derivative of r with respect to t, is df dt I plus dg dt j plus dh dt k. In other words, we compute limits and derivatives component-wise. Well, what that means in particular is breaking everything down in components, we can derive all the usual rules for limits and derivatives in terms of components, or we can use the definitions and get them directly. But in any case, just to review, for instance, we have rules like limit of the sum equals the sum of the limits, limit of a product equals product of the limits. And here, in the case of vectors, what kind of products are we talking about? Well, we can have the dot product of two vectors. So if we had vector functions r and s, we could have the dot product of R and S, or I could have scalar multiplication, so a scalar function times a vector function, or we could have the vector product, or sometimes called the vector cross product or cross product. In other words, any one of these form of products, the limit of the product will be a product of the limits, and consequently, if each of the factors is continuous at a specific point, then the product will be continuous at that point. And so dot products of continuous vector functions are continuous. Continuous scalar function times continuous vector function is continuous. Vector cross product of continuous vector functions is continuous. Sum of the continuous vector functions is continuous. And these rules give us the rules for differentiation, and they're very similar. So for instance, you ordinarily know that when you differentiate a sum, you just differentiate term-wise. The same thing happens here. If I have R plus S to differentiate, we just differentiate R, differentiate S, and add the results. How about to differentiate R dot S? Here, the usual type product rule works. That is, the derivative of the first factor dotted into the second factor plus the first factor dotted into the derivative of the second factor. Same thing happens with the cross product. The cross product, the derivative of the cross product is the derivative of the first factor cross the second factor plus the first factor cross the derivative of the second factor. Likewise, if I have a scalar function times a vector function to differentiate, that would be the derivative of the scalar function multiplied by the vector function plus the scalar function times the derivative of the vector function. The essential ingredient in all these things which make these vector product rules work is simply the fact that the multiplication is distributive. That is, with any one of these multiplications, the distributive law works for either factor over the other. And so consequently, these are very useful facts to keep in mind. For instance, a very interesting fact which we can derive from that is that if R is a differentiable vector function of t of constant length, then R dot dr dt equals 0. Let me put a little arrow on that just to emphasize this is vector functions here. And this is a useful fact to observe because it follows directly from the product rule for differentiating dot products. So if R has constant length, we can write length of R of t as a constant c. Well, consequently, if I square that, it's still constant, but the square of the length, remember, is the dot product of the vector function with itself. So now let's differentiate this using the product rule. So the derivative of the constant is 0, but the derivative of the dot product, well, that would be R prime dot R plus R dot R prime. Well, the order of the dot product doesn't matter, so this is 2R dot R prime. Consequently, if 2R dot R prime is 0, R dot R prime equals 0, which is the same as saying R dot dr dt equals 0. Now, to say that the length is constant means, in effect, that once the tail of the vector is fixed at the origin of coordinates, that constant is the radius of a sphere on which the tip of the vector is moving. So imagine here we have a sphere in space of radius c, and this tip of the vector is constrained to be on it at all times. So the curve of motion is some curve on this sphere, and what we're saying then is that at each instant the velocity vector must be perpendicular to the radial vector. Well, you can see on the sphere that if I'm perpendicular to the radial vector, I'm tangent to the sphere. So in each case, if I'm moving on a sphere, then at each instant, my velocity vector must be tangent to the surface of the sphere itself. Well, let's find velocity and acceleration for a vector function. R of t is the position of a particle in space at time t. Find the particle's velocity and acceleration vectors, then find the particle's speed and direction of motion at the given value of t. Write the particle's velocity at that time as the product of its speed and direction. Of course, acceleration is just the derivative of velocity, and so consequently, when we're presented with a vector function and we need to find velocity and acceleration, v is the derivative of the vector function, and then the acceleration is the derivative of v. Here we want to work at t equal 1. Our vector function is r of t equals t plus 1I plus t squared minus 1j plus 2tk, and so we can differentiate component-wise. The velocity is, well, derivative of t plus 1 is simply 1, so we get I. Derivative of t squared minus 1 is 2t, so that's to be multiplied by j. And then the derivative of 2t is simply 2, so we have 2k. So our velocity is I plus 2tj plus 2k. And so consequently, the acceleration being the derivative velocity, well, that's constant. Its derivative is 0. Derivative of 2t is simply 2, so we get a 2j. That's constant. Its derivative is 0. So the acceleration itself here is a constant vector, 2j. So now, what's the value of velocity at t equals 1? Our velocity at time 1 is I plus 2 times 1 times j, which is 2j plus 2k. What's our speed? Well, remember the speed, that is the length of the velocity. So that's the square root of the sum of the squares of components. 1 plus 2 squared is 4, plus another 2 squared is 4. 1 plus 4, that's 9. We have square root 9 is 3. There's our speed. How do I get a unit vector which points in the direction of our motion? Well, I simply take the velocity vector and divide by the speed. In other words, when I take the velocity vector and divide by its length, I arrive at a unit vector. So let's call that u. That's equal to 1/3 v. So that's 1/3 I plus 2/3 j plus 2/3 k. Our acceleration vector, 2j, our unit vector in the direction of motion, 1/3 I plus 2/3 j plus 2/3 k, and our speed is 3. Notice if I multiply speed times the unit vector in the direction of motion, we get back to the velocity. Well, let's use differentiation to calculate velocity and acceleration for a vector-valued function. Here I have the vector-valued function r of t equals 2 cosine ti plus 3 sine tj plus 4tk. So remember, to get the velocity v, all we do is differentiate the vector-valued function. Derivative of cosine t is negative sine t, so our first component will be negative 2 sine t I. Derivative of sine is cosine, so our second component is 3 cosine t j. And the derivative of 4t is simply 4, so the last component will just be 4k. And to find acceleration, we differentiate again. The acceleration at time t is simply the derivative Here, the derivative of sine is cosine, so we'll have negative 2 cosine t I. Derivative of cosine is negative sine, so the second component becomes negative 3 sine t j. And now that component is constant, so its derivative is 0. So our acceleration only has I and j components. In effect, the acceleration vector now we see has to be horizontal. Well, what about the velocity at time pi over 2? The sine of pi over 2 is 1, but the cosine of pi over 2 is 0. So the velocity at pi over 2 is equal to negative 2I plus 0j plus 4k. And so consequently, the speed, being the length of the velocity vector, well, that's the square root of the sum of the squares of the components. That would be the square root of negative 2 squared is 4, plus 4 squared 16, that's square root 20. So a unit vector in the direction of our motion at time pi over 2 would be negative 2 over root 20 times I plus 4 over root 20 times j. And what's the acceleration at that instant, pi over 2? Well, cosine pi over 2 is 0, so the first component vanishes. Sine of pi over 2 is 1, so we'll have negative 3j. Well, the dot product of vectors can be used to encode all the geometric information and situations we have to deal with. We know, for instance, that distance is length of vectors, and length of vectors is the square root of the dot product with itself. Consequently, we can get lengths and distances out of the dot product of vectors. We can also get angles. Let's review briefly the formula. The angle between vectors A and B, denoted theta, is given by cosine theta equals dot product of A with B divided by the product of the lengths. So anytime you want to find the angle between two vectors A and B, just take their dot product, compute each of their lengths. Notice to compute the length of A, we take the dot product of A with itself and then take the square root. Likewise for the length of B. And so consequently, dividing the dot product of A with B by the product of the lengths, we have to get a number that's between -1 and 1, because the dot product of two vectors will always be between the negative of this product and this product. In other words, it is the case geometrically that always the absolute value of the dot product of A with B is less than or equal to the product of absolute values. And so consequently, this number has to be between -1 and 1, and so is the cosine of an angle theta. Well, let's look at an example. R of t is the position of a particle in space at time t. Find the angle between the velocity and acceleration vectors at time t equals 0. Here, I have the vector function r of t equal 3t plus 1i plus square root 3tj plus t squared k, and I want to find the angle between the acceleration and velocity at t equals 0. So we begin by computing velocity by differentiating. Velocity at time t, derivative of the first component is simply 3, so we have 3i. Derivative of the second component, square root 3t, will just be square root 3, so we have square root 3j, plus the derivative of t squared is 2t, so the last component is 2tk. Now the acceleration is derivative of velocity, so the acceleration at time t, well, the first second components, notice they're all constant, so that's a big constant vector. Its derivative is 0. Derivative of 2tk is simply 2k. So there's our acceleration vector. Now what happens when we put t equal to 0 here? V at time 0, well, putting t equals 0 wipes out this k component, and we just get 3i plus square root 3j. Well, now it's easy to see that these vectors are perpendicular because k dot I is 0 and k dot j is 0. And so consequently, for the dot product, we get 0. What does that tell us? Remember, whenever the dot product of two vectors is 0, that's telling us the vectors are perpendicular, because remember the cosine of pi over 2 is 0. So this tells us A is perpendicular to V at 0. The angle between them is pi over 2. Well, let's use derivatives of vector functions to actually get a parameterization of a tangent line to a curve in space. The tangent line to a smooth curve r of t equals f of ti plus g of tj plus h of tk at time t equal t naught is the line that passes through the point f of t naught, g of t naught, h of t naught, parallel to v of t naught, the curve's velocity vector at t naught. Because remember, the velocity vector is always tangent to the curve, and so consequently the tangent line will be parallel to the velocity vector. Find parametric equations for the line that is tangent to the given curve at the given parameter value t equals t naught. Here I have the vector valued function r of t equals sine t I plus t squared minus cosine t j plus e to the tk. We want to consider the point t naught equals 0. Find capital T of t, which is equal to the parametrization of the tangent line to r at time t equals t naught. So remember, if we have a straight line, we can always have a parametrization t of t in this form. Here's what we're looking for. We want some vector A plus t times a vector B. Here A will be a vector which touches the line, and B is a vector pointing in the direction of the line. So consequently, we want our line to be tangent to this curve at the point t naught. And so the vector touching the curve at that point t naught will be the A. So we're going to take A equal r at time t naught. And for the vector pointing in the direction of this tangent line, well, remember the velocity vector is tangent to the curve of motion. So we'll take B to be the velocity at time t naught. Now here t naught, remember, is 0. So this will be the velocity at time 0. A will be r at time 0. So for instance, what is r at time 0? Sine of 0 is 0. Cosine 0 is 1. 0 minus 1, that'll be a negative 1. E to the 0 is plus 1. So r of 0 will simply be negative j plus k. Now let's differentiate to get the velocity as a function of time. V of t, well, derivative of sine is cosine. So we have cosine t I plus derivative of t squared is 2t minus the derivative of cosine, well, minus the negative sign would be plus sine t j, and plus the derivative of e to the t is e to the t, so we get e to the tk. What's going to happen when I put t equal to 0 to get the velocity at time 0? Cosine 0 is 1, so we get I. 2 times 0 plus sine of 0, well, sine 0 is 0, so that is all 0. E to the 0 is 1, so we just get k. So our velocity at time 0 is simply I plus k. Our position at time 0 is negative j plus k. So A is negative j plus k, and B is simply I plus k. So I've written that down on a new sheet. Let's now compute our parameterization. So A, vector A, is negative j plus k. Vector B we've computed as I plus k, and our parameterization T of the tangent line is simply A plus TB. So that means we get negative j plus k plus T times I plus k. And so let's collect components together and write them in usual order. So we have T times I. There's no j over here, we just have negative j. And for k we have 1 plus T all multiplying k. So there is the parameterization of the tangent line to this function r of t at the point time t equals 0. And here, that's the t naught equals 0 for r of t. So notice this is a vector function of time t, but this is not the same function as r of t. This is the tangent line to this curve at the instant t naught equals 0. If I wanted this, for instance, in ordinary coordinate parametric form, this says x equals t, y equals negative 1, and z equals 1 plus t. Well, we've looked at some problems involving vector functions. Remember, the best way to think of a vector function of a single real variable is as a motion. So the derivative then is representing velocity. It's tangent to the curve of motion, and its length gives the speed. The derivative of velocity is then acceleration. Remember, it's useful to know that when a vector function has constant length, its derivative has to be perpendicular to the position vector. So for instance, if the speed is constant, then the velocity and acceleration will be perpendicular. Well, now that you've seen these problems work, you should try some on your own.